Hey everyone, welcome. Look, if you're diving into coding challenges or, prepping for those big tech interviews, then you already know data structures are everything. And today, we're going to master one of the absolute cornerstones, the singly linked list. We're going to start with the basics, but then we'll get into the really clever patterns, the kind that can seriously make or break an interview.
So let's just imagine for a second, you need a list of something, but you have no idea how long that list is going to get. If you use a normal array, what do? You have to guess a size, right? And if you guess too big, you're just wasting space. If you guess too small, well, that's a total disaster. So how do you build a list that can just, grow and shrink whenever you need it to? Well, that's the exact problem linked lists were built to solve.
All right, let's dive in. We'll start at square one. What exactly is a linked list when you get right down to it?
It's actually way simpler than it sounds. Just picture a chain, that's it. Each link in that chain is what we call a node, and every single node is only holding two things. First, some piece of data, we call that the value, and second, a pointer. Think of the pointer as just an arrow that points you to the very next link in the chain. And the whole thing kicks off with something called the head. That's just our starting point, a pointer to the very first node. From there, it's like a treasure hunt. You just follow the next pointer from one node to the next, and you keep going until you hit a pointer that leads to, well, nowhere. A null pointer. That's the universal sign that you've reached the end of the line. Okay, comparing this to a standard array is super important. With an array, you can just jump straight to any element you want, right? You just use its index. Boom, you're there. But with a linked list, you can't do that. You have to start at the head and walk the chain, one step at a time. That's what we call sequential access. So why would we ever give up that speed? Well, in return, you get this incredible flexibility. The nodes can be scattered all over your computer's memory, which lets the list grow and shrink super easily. It's kind of like a music playlist. You can just drop a new song right at the top without having to move all the other songs around. It's so much simpler. Okay, so we've got the what. Now let's get into the how. Let's talk about the actual mechanics of working with these things. So let's take one of the most common things you'll do, adding something new right to the front of the list. It's this simple, really elegant three-step dance. Ready? Step one, you make your new node. Step two, you tell its next pointer to point to whatever the old head of the list was. And step three, you just announce that your shiny new node is now the new head. That's it, you're done. And here's the real magic. That whole operation, it takes what we call O1, or constant time. Now, what does that mean? It means it takes the exact same tiny amount of time whether your list has 3 items or 3 million. It doesn't matter how long the list is. This speed is a massive advantage. It's actually why linked lists are the backbone for other really important data structures, like stacks, where you're always adding and removing from the top. This table really lays out the big trade-offs, doesn't it? Look, inserting at the head is lightning fast. That's our O of 1. But check out searching for something or trying to add a new node at the very end. That's O of n. That n stands for the number of items in the list. It basically means you have to walk the entire chain to get there. So the bigger the list, the longer it takes. That's the trade-off right there. All right, now for the really fun stuff. We're moving beyond the basics. Linked lists are the key to some super clever problem-solving patterns. I like to call them the magic tricks. And trust me, these are the exact kinds of things that pop up in technical interviews all the time. Okay, let me hit you with a classic puzzle. You've got a links list, right? But here's the catch. You're only allowed to go through it once. Just one pass. So how on earth could you find the exact middle node if you don't even know how long the list is to begin with? It sounds totally impossible, but the solution is, well, it's beautiful. It's called the tortoise and hare method. You set up 2 pointers. The first one is our tortoise, the slow pointer. It just plods along, one node at a time. The other one is our hare, the fast pointer. It's zipping ahead, moving 2 nodes at a time. So what happens? By the time our speedy hare gets to the very end of the list, guess where our slow and steady tortoise is? Yep, right in the middle. It's such a clever, super efficient way to solve it in a single pass. Okay, here's another big one, reversing a linked list. This sounds easy, but it's tricky. The secret is all in how you juggle 3 specific pointers: previous, current, and next. It's a delicate dance, because if you mess it up, you can accidentally break the chain and poof, the rest of your list is just gone forever. So here's the recipe for that pointer juggling. You're going to loop through the list, one node at a time. And for every single node, you do this. First, you save a reference to the next node so you don't lose it. With that safe, you can now reverse the current node's pointer so it points backwards. Finally, you just scoot all your pointers one step forward. You just repeat that little sequence over and over, and when you get to the end, that previous pointer you were tracking, that's the new head of your perfectly reversed list. All right, let's bring this all home. Why are we spending all this time mastering these ideas? What's the practical takeaway here? It's because this is what you're going to see out in the wild, and especially in coding interviews. Seriously, reversing a list, finding the middle element, detecting if there's a cycle, merging two sorted lists, these aren't just, textbook problems. These are the standard questions that companies use to see if you really understand how to work with data. So as you're practicing, please keep these common mistakes in mind. The number one rookie error is trying to access something on a null node. That's an instant crash. Also, here's a pro tip for you. Sometimes using a dummy node right before the head can make your insertion and deletions code way simpler. And the biggest warning of all, remember what we said about reversing? Always save your next pointer before you start changing things. So let's wrap this up with a little challenge to get you thinking. You now know how to reverse an entire list, right? But what if you had to adapt that same logic to reverse it in chunks, like, say, in groups of 3? That's the next level of problem solving that these fundamentals open up for you. Give it some thought. Thanks for joining me.